So this next chapter deals with chemical and phase equilibrium. First we'll talk about the thermodynamics of equilibrium. Up to this point we assumed that all the reactants are converted to products. But now we have a balance where there will be some quote-unquote reactants still in the final mixture, and it won't have gone all the way forward, complete combustion or complete reaction. So we'll talk about the compositions, the final equilibrium compositions having some quote-unquote reactants as well as products in them. And then we'll talk lastly about phase equilibrium. This chapter is built on the property known as Gibbs free energy, or it used to be Gibbs available energy, or Gibbs energy, different names for it. It's a thermodynamic property just like enthalpy, internal energy, entropy. It was defined a long time ago, true? See that? By Josiah Willard Gibbs, hence it's his name attached to it. It's used to predict whether a process will occur spontaneously at a constant temperature and pressure. And if it's not going to occur spontaneously, well then it's non-spontaneous, and it's also used to predict when it's in equilibrium. Here's the definition. You'll see it written in textbooks as G is defined as H minus Ts. Well, just like H was defined as U plus PV, true, you have a new property G, Gibbs free energy, defined as H minus Ts. I think we understand all of those terms in the equation. H is enthalpy, T absolute temperature, S entropy. A lot of times you also see it written this way, and I think it's probably better written this way for our application. The change in the Gibbs function is equal to the change in the enthalpy minus the temperature times the change in the entropy. I know that's an application, but this is the way we apply it often in this form right here. Because we'll take a look at the change in the Gibbs free energy is a maximum non-expansion work. That's the interpretation of it. It's the maximum non-expansion work possible from a reaction process that occurs at constant temperature and constant pressure. So if I have this is the way we apply it. If I have a system, it's undergoing a reaction process or a process, and that process is at constant temperature and constant pressure, we can interpret delta G, or more importantly, I should say, or more precisely, the negative of delta G as the maximum non-expansion work. So what does this remind you of, this maximum non-expansion work? Another property we started this chapter studying. Doesn't it sound like exergy? Yeah, maximum useful work. So it's very similar to that. All right. Well, what we do is it's used is if delta G is less than 0, it's a large negative value, then we say that the reaction process is spontaneous, or its forward reaction is favored. Now, the forward is going from reactants to products. So reactants to products is favored. And then just the opposite, when it's not less than 0 but it's greater than 0, then it's not a spontaneous process. It's not going to move in that forward direction, but actually the backward reaction is favored, because you could write the reaction equation flipping sides, right? Make the right go to the left, left go to the right. And then just a little bit in between, you can think, okay, well, what happens when the change in the Gibbs free energy is 0? Well, that's when it's at equilibrium. And so you have an equilibrium mixture of some reactants and some products. Let's just develop this idea a little bit. That the change in the Gibbs free energy is the maximum non-expansion work for a process at constant temperature and pressure. We're studying reaction processes. Reactions. So think of the system that starts with initial state Often we use the symbol 1 for the initial state. And it undergoes some sort of reaction process, and it goes to a final state. Often we use the number 2 for the final state. So initially, we had what we call reactants, and finally we have products. All right. Now, it's at constant temperature and pressure. That's part of the definition right here. So if you say, okay, it starts at P1, it'll end at P2 where the final pressure is the same as the initial pressure. And if it starts at T1 and the final temperature is equal to the initial temperature, then T2 is equal to T1. So I'm just emphasizing that it's under constant pressure, constant temperature process. So let's apply the first law of thermodynamics for a system, a closed system, undergoing a process from initial state 1 to final state 2, neglecting changes in kinetic and changes in potential energy. So we're left with the equation that U2 minus U1 is equal to Q, and I'm going to emphasize that that's our in minus W out. You like that equation? It goes way back. We've been working in thermodynamics now for 2 semesters, so that goes way back. And the work out, we can think, I want to bust it into 2 components, a useful workout and a non-useful part, which is the boundary, pushing back the boundary. Okay, that would be a non-useful. Same with exergy, same type of description with exergy. We have a non-useful pushing back the boundary. So I'll just say useful plus boundary. What about this boundary work? How can you describe this boundary work? Well, it's happening at constant pressure, isn't it? Is the boundary work equal to the integral P dV? Is that equal to P times the final volume minus the initial volume? If you have no volume change, you have no boundary work. And it's constant pressure, so it's just P dV. So we're interested in rewriting the first law in terms of the useful work is equal to, just algebra, the heat transfer in during the process minus a change in enthalpy, where that change in enthalpy is U plus PV. Did I do the algebra okay? Should I give you a minute, or should I fill in more steps? Does it look good? All right. Okay, so let's go now to the second law and write the second law for this process. How would we like to write it? Well, how about the change in the entropy, so S2 minus S1. How can the entropy have increased in the system? Well, if I have some Q coming in divided by some temperature of the boundary that it comes in at. Now, we have an isothermal process. T1 is equal to T2. So guess what? I know I could write this as an integral of del Q over TB, just like we could write the boundary work as integral PdV, but this is just Qn divided by the temperature that's constant. Okay. Is there any other way that the entropy can increase? What term is missing out of the second law? Entropy production, and so we would write it maybe as sigma 1 to 2. True? That's our notation in the textbook. So it's the amount of entropy that's produced in the process. Let's go ahead and rewrite this second law. So Qn for this problem, where it's isothermal, is equal to T times S2 minus S1, or delta S, minus T times sigma. Did I do that okay? Guess what you do with that Q from the second law? You go back to the first law and eliminate Q. So this equation now becomes, I'm going to eliminate this Q right here, go right there, boom. Hence, what we pick up is we pick up that the work useful is equal to, I'm going to put minus H2 minus H1, leave that term right there, and then we'll pick up a plus temperature S2 minus S1, or change in S, minus a temperature and the entropy generation due to irreversibilities. If we want this to be a maximum, what do you think happens to the sigma? Goes to 0, and it'll give us a maximum. So I need to fit it in somewhere. Let me try and not scroll down. I'll fit it in right over here. So jump over here. So we have that the work useful, the maximum useful work is equal to, I'm going to put a minus, and then I'm going to bring out here, I'm going to have a change in H minus T change in S. So it's the negative of the change in the Gibbs free energy. That grouping of terms, that grouping just called G. So by definition, delta G is delta H minus T delta S. Now, if we have a reaction equation, what do you think delta H is? It's that change in enthalpy. We were able to calculate that from last chapter. It's going to be typically, not positive, negative for an exergetic process, right? Like a combustion process. All right. And then what about this term? Well, typically things that mix or things that go forward have an increase in entropy. But could I have a reaction where the delta H, let's see, if it's less than 0, it's exergetic. It gives off heat. Could you have a delta H where it's greater than 0? Well, it's not exergetic. What is it? That's what? Another word. What's it? It absorbs heat. The products will be cold, right? Colder than they started because it wants to absorb heat from the surroundings. Instead of, I'm just tripping on my words here. What is that word? What is it again? Yeah, something like that. Man, I'm embarrassed. What is that word? It's like, when you talk about when it gives off heat in the reaction, or then it cools off, the products are colder. It absorbs heat. What is it? Something doesn't sound right. I can't place my finger on it. Maybe you're all right and I'm just off today. But also, you can have a reaction where this is the change in entropy is a measure of disorder. It's pretty easy for things to become less ordered or more disordered, right? So it's often, it's easy to have this as positive. But you can also have a reaction where it becomes more ordered. So if you have more components combining to fewer components, then it would go from more disorder to less disorder. It would become more organized. So you can have a whole host of things if it's, did I say exergetic? No. Exergetic. That must be the term I'm thinking of. I don't know why it's not clicking today. So yeah, it's one where it gives off heat or absorbs heat. So it gives off heat and is more disordered. It's very highly favored in the forward direction. It's going to go. But you can also have one where it absorbs heat, but it becomes very disorganized. It'll still be favored, but it's more unique. You don't see a lot of reactions like that, right? It's like you put things together and they go forward, the reaction occurs, and it gets cold. There's a few of those reactions that they make that are in your textbooks in chemistry. And then some other reactions are, well, it gives off heat, but it becomes less disordered. That works well at a certain temperature. So if you're above that temperature, great. If you're below that temperature, not so great. Okay? All right. Well, you could take a look at this Gibbs free energy. There's a lot out there. Here's a Wikipedia site. It's again, let me just emphasize, it's the maximum amount of non-expansion work, so they take off that expansion, non-useful component pushing back the boundary, that can be extracted from a closed system, and the maximum can be attained only in a completely reversible process, so that was sigma equal to 0. So how do we use this now to establish when our mixture is in equilibrium? It doesn't want to go forward anymore, but it doesn't want to go backward either. So it's in an equilibrium state. Well, I'm glad you asked, and there's the derivation. It's one of these derivations that are in your chemistry textbook as well as in this textbook. But instead of trying to do it, let me just summarize it and encourage you to read it. So you just have equilibrium equations, thermal balance, mechanical balance, and then the composition. That's what's new. You have a reaction equation and you have a balance in the composition. You go to, what does this equation look like? First law for an infinitesimal change, you rewrite it. There's that boundary work. You have an entropy balance. You combine them. All real processes, the delta sigma, the entropy production is greater than 0. But you have a term here for all these processes. That's just changes in properties. So if you have a chemical and phase equilibrium at constant temperature or fixed temperature and fixed pressure, introducing the Gibbs function, the change in the Gibbs function using calculus, you find that for constant pressure, constant temperature, the change in the Gibbs function has to be less than or equal to 0. It's a negative sign, reverses the inequality. And so that's the way they'll write it. They'll say the equilibrium criteria is that the Gibbs function doesn't change at that point for the temperature and pressure of equilibrium. So you have a minimum in that Gibbs function G. So maybe they're showing you over to the right or to the left. Well, it would work, if it was to the right, it would work backwards to get to the equilibrium state, or if it was to the left, it would work forward. Well, that's not the end of the story, because we have to talk about a system that has multi-components. There's been a reaction, and so we have some reactants and some products in equilibrium. So they expand the concept of the Gibbs function as a function of temperature, pressure, and all of the components that make up that mixture. And the Gibbs function can be, and I'm skipping some steps here, the sum of the amounts times the rate of change of the Gibbs function with respect to the amount, holding temperature, pressure, and all the other components constant in that partial derivative. Define that chemical potential. That's just the derivative of the Gibbs function. So the Gibbs function can be written as the sum of Ni mu sub i's, which is the chemical potential. And so at the equilibrium criteria, it's equal to 0. You can express the molar enthalpy of the mixture, or using the molar enthalpies to get the enthalpy of the mixture as well as entropy of the mixture. Hence, this is where you can calculate the Gibbs function of the mixture. And you introduce the Gibbs molar function, G bar, just like H bar and S bar, we deal with ideal gases. I know that sometimes we'll have a liquid fuel and we're studying combustion, but if for ideal gases that the total Gibbs function is sum the amounts times the molar Gibbs function, the molar Gibbs function equal to the chemical potential. All right, so the chemical potential, you have H minus TS, not bar, plus this term right here. Doesn't that look like our entropy? Isn't that our how entropy is a function of pressure? Here is just the entropy is a function of temperature. Here's how the entropy is a function of pressure. And they split that T to multiply both terms. All right. So for an ideal gas, you have the chemical potential is this Gibbs molar function at standard state plus this term for ideal gases. We're almost done. One more dense slide. Here it is. So our general case for a reaction equation is written in this form. What is A? What is B? What is C? What are D? Those are our components. How come they didn't write it where there's 1 going to 2 or 2 going to 3? Well, this is the general case where 2 goes to 2. You have an arrow like this. What's that indicate? That's not complete combustion or complete reaction where it's so forward favored that it all goes to products and there's no reactants left. Sometimes I'll write it like this, meaning that you have in an equilibrium, some of the A's and B's are being converted to C's and D's, but some of the C's and D's are being converted back to A's and B's, and so now you're in balanced state. Okay, that's the notation in chemistry. What are the nus? Those are the stoichiometric coefficients in our balanced reaction equation. Okay. Well, you talk about an extent of reaction such that if I have a production of C, that's going to come at the destruction or consumption of A and the consumption of B. And they're related by the change in C to the stoichiometric coefficient in C and change in D to the stoichiometric coefficient in D. So this is one of these run-on equations. There's 1, 2, 3, 4 equal signs, right? So if some A or B is consumed, they're consumed in the right proportion to each other, and they produce the right proportion of C and D based on those stoichiometric coefficients. So the change in A is equal to minus nus of A times the extent of the reaction, d epsilon. You want to get rid of that d epsilon, put it into the equilibrium criteria. You have the d epsilon, then you can cancel it. And so the equation of reaction equilibrium is you have the stoichiometric coefficient times that molar Gibbs function, mu, and that molar Gibbs function expanded for ideal gases, dot, dot, dot. And when you combine terms, you combine everything that's a function of temperature on one side and the function of pressure on the other side. And you rewrite the equation. I guess I lied. There's 2 more dense slides, isn't there? This one is, I think, is the last. And you have the change in the molar Gibbs function at standard conditions divided by R bar T is equal to the natural log of, and then what is this y sub C? Well, that's the same y sub C that was up there. What was that? That's the mole fraction of the component C in our equilibrium mixture. And what is it raised to the power? Nus of C from the algebra. Then you have y sub D raised to the exponent power nus of D, and you divide it. And then you have this term right here in parentheses, P divided by P ref. Our reference pressure is 1 atm. I was looking at something the other day, and they said some international community of chemists voted to redefine the reference pressure, and it's 1 bar now. But I didn't go verify it. So a lot of textbooks still have the reference pressure as 1 atm. What's the difference? Not much between 1 bar and 1 atm. And you have all these stoichiometric coefficients. And in chemistry then, this term over here is described as the natural log of K, an equilibrium constant K. And that equilibrium constant K, just like this term over here, is a function of temperature only. So this is the equilibrium equation. So you take the exponent of both sides, so you get rid of this natural log and natural log. So you have the equilibrium constant, which they emphasize is a function of temperature. It's not multiplying temperature, it's just say, hey, this is a function of temperature, is equal to the mole fractions raised to the exponents, the pressure of the mixture divided by the reference pressure, all of that to an exponent. How many people have seen something like this in their chemistry class? All hands go up. Yeah, all hands are up, right? How many people wish they'd never seen? No, I don't know. Keep your hands down. Does it make sense? All right. Now they can take this equation, it's in mole fractions, and you can also rewrite it this way. Same equation. What did they do? Well, instead of y sub c, they wrote it as n sub c. But what is n sub c divided by n total? Isn't that y sub c? So the number of moles of C divided by the number of moles total is the mole fraction. So they said sometimes it's easier to work not in mole fractions, but in total number of moles of each component. But then what happens here, you have to have that N where you didn't have it up here. Okay, so basically you get the N sub C is divided by N is your Y sub C. All right. So sometimes it's like, hold it, I understood this equation. Where did this equation come from? Well, they're the same equation. It's just rewritten in a more convenient form for some problems. Where do you get these equilibrium constants K? In table A27 of our textbook, they have a number of reactions that are described. Here's a reaction. What is that one? It's H2 dissociates to two H's. Dissociation of hydrogen. Let's take a look at this reaction. What is this one? This is 1/2 O2 plus 1/2 N2 produces NO. Okay. What's this reaction? CO2. So maybe I would write it like this. CO2 goes to CO plus 1/2 O2. They don't give you a lot of reactions. This is it. So this is our only table of reaction equations with the equilibrium constants reported in our textbook. Now, the equilibrium constant is reported as the base 10 or the log base 10 of K. So this is what they're giving you in these numbers. Let's say this number or that number right there. It's log base 10 of K. So let's say I'm interested in this reaction equation, which is the dissociation of carbon dioxide and the carbon monoxide and oxygen. And I'm interested in it at a temperature of 3,000 Kelvin. Well, I would come to the table, I would grab that value. The log base 10 of that of K is equal to negative 0.485. So guess what K is? K is 10 to the minus 0.0485. And there you go. Okay. Let's take a look. Why is this a function of temperature? Well, back in our equations, what they did was they separate everything that's a function of temperature on one side, and then they separate the compositions on the other side, or the mole fractions on the other side, okay, and the pressure on the other side. So you can find these equilibrium constants, and they're temperature dependent. Once I do that, then I can go back to the equation here and maybe find the equilibrium composition of whatever C, D, A, and B are in my reaction. So let's start out with this problem. We have 2 kilomoles of carbon, and it reacts with 3 kilomoles of oxygen, O2. to form an equilibrium ideal gas mixture of carbon dioxide, carbon monoxide, and oxygen. There's no nitrogen present, there's nothing else. It's just in a container, just only carbon and oxygen, and the equilibrium mixture has only CO2, CO, and O2. That's it. And it's at 3,000 Kelvin. And it's at a pressure of 3 bar. Calculate the equilibrium composition of the gas mixture. Well, you go back to our general reaction equation, and then you deduce what type of reaction equation we have. And when you come to our table here, you need to pick one. This is the one you're going to pick. This one right here. That's what's happening. Okay? So make it look like the general reaction equation. So instead of A, I'll have CO2. And we'll have 1 mole of CO2 disassociates into 1 mole of CO and 1/2 of mole of oxygen. Did I write this equation down correctly from the table, for disassociation of CO2? Check it. Is the carbon balanced in it? Is the oxygen balanced in it? Okay. Now, what about this? Well, it's 1 times 0 or 0 times 1 or something. It's 0 times 0 for this B. There's nothing for the B. Okay, so I know they wrote it down where there's 2 reactants, 2 products, but here I have an example where there's just 1 reactant and 2 products. So it's just the B is not existent. Okay. So anytime I see nu sub A, I'll say, that's 1. Anytime A, that's CO2. Anytime nu sub C, that's 1. Anytime C, that's carbon monoxide. And I know that can be confusing because they use A, B, C, D for which entities there are. Now we have CO is C. Oh, sorry, but yes. This is our general equation, and we wrote it from this right here, and there's only one thing, A, on the left-hand side. There's no B on the left-hand side, and this is C, and this is D on the right-hand side. That makes sense? Okay. So this is 1/2. Notice the nu sub D is 1/2. That coefficient, stoichiometric coefficient's 1/2, and this is oxygen. Well, I wrote down our equilibrium equation right here. Okay? So what I'm going to do is I'm going to say, I go to that table, and we already found what K was. It was 10 to the negative 0. I forgot the value. 485. 10 to the 0.485, right? So that's what K is. If you have a calculator, you can run it and you get a number for K, right? Some number. So that number is known on the left-hand side of our equilibrium equation. And now we just write down, I need the number of moles, the number of moles of my C component. That's the number of moles of carbon monoxide raised to the 1 power times the number of moles of the D component, which is the number of moles of oxygen, O2, raised to the 1/2 power, divided by the number of moles of my A component, which was carbon dioxide, raised to the 1 power, and then forget the n sub B raised to the nu sub B. It's just like you could put 1 raised to the 0. It's just 1. Leave it out. Then you're going to multiply the actual pressure, 3 atm, divided by the reference pressure, 1 atm, divided by the total number of moles present. Well, that's going to be the number of moles of carbon monoxide in equilibrium, the number of moles of diatomic oxygen in equilibrium, and the number of moles of carbon dioxide in equilibrium. That's N total. So you sum them all up, right? And then it's raised to the the power of nu sub c. Nu sub c was 1 plus nu sub d 1/2 minus nu sub a minus 0. Hey, I didn't invent this. I'm just trying to, explain it the best I can. How many people remember doing problems like this? All hands are up. I'm glad to see that. All right, so this a lot of times this, this will reduce to something like 1/2, or if it reduces to 0, guess what? Pressure has no effect on the equilibrium mixture. All right. Okay. So now I have a problem. I have one equation with how many unknowns? I have the unknown, the number of moles of carbon monoxide, the number of moles of oxygen, and the number of moles of carbon dioxide in equilibrium. How many unknowns? 3 unknowns. But I only have one equation. I need more equations. That's where this information that we have 2 kilomoles of carbon, period. Right? So I'll come and I'll write, this is my equilibrium equation, and then I'm going to write a carbon balance equation, and then I'm going to write an oxygen balance equation, and then I'll get 3 equations with my 3 unknowns. I know they're nonlinear. I know they're not nice, but at least we have a fighting chance of solving it. So for my carbon balance, think about it. The number of moles of carbon total to start with has to be equal to the number of moles of carbon at the end. So I have the number of moles of carbon monoxide in the final equilibrium mixture plus the number of moles of oxygen in the final equilibrium mixture and the number of moles of carbon dioxide equilibrium mixture. This one has, for every mole of carbon monoxide, I got 1 mole of C. For every mole of oxygen, I get no moles of C. And for every mole of CO2, I get 1 mole of C. So we're left with the equation that says 2 is equal to NCO. You can throw this one out because it's 0 on the coefficient, plus N of CO2. That's from a carbon balance. How about the oxygen balance? I recommend you do the O balance, not the O2 balance. So how many, if I have 3 kilomoles of O2, how many do I start with for O? I start with the number of moles of O is 6. And how many do I get for every mole of CO? 1. How many do I get for every mole of O2? 2. How many do I get for every mole of CO2? 2. Makes sense? So 6 is equal to NCO plus 2 NO2 plus 2 NCO2. Does that make sense? I'm sorry? This equals 5 or 6? This 6?
It should be 6, but the right side equals 5.
Yeah, so what we have is, it's like this is X, this is Y, this is Z. So 6 is equal to X plus 2Y plus 2Z. Now go find X, Y, and Z. Right? Maybe we should use X, Y, and Z as my unknowns. But then it adds another, what was X again? Well, X was the number of moles of CO. What was Y? Number of moles of O2. What was Z? Number of moles of CO2. All right, what I'm going to do is I'm going to go ahead and stop here because I think I'll pick this up and I'll solve it, okay? But this is one equation. There's another equation. And there's my third equation, right? And I have 3 unknowns. Take the last 2 equations and pick one guy to live, so to speak, and eliminate the other 2 and get then one equation where there's only one unknown in it. Do you want me to? well, okay, let me do it very quick, but I don't have much time. Let's say I want to solve for the number of moles of CO2. So when I see NCO, I just replace it by 2 minus the number of moles of CO2. So I'm going to get rid of NCO every time I see it. Just get rid of it. So up in here, right there, replace and replace right there. How about for the next one? Well, I do this. I have the number of moles of O2 is equal to 3 minus the number of moles of CO divided by 2 minus the number of moles of CO2. Did I do that math right? So I use the third equation. Anytime I see number of moles of O2, I'll replace it by that. But then I have to use this one right there to get rid of the NCO. Make sense? I'm going to leave it. I'm going to stop right there, and I'm going to pass back the exams.